Fine. So I have started recording also. And this is today's topic that we are going to start with. So till now we have discussed about processes, right? What is process? What is the manifestation of process in the system and all those stuff. We discussed PCB, we discussed different elements of process image. And then we also discussed a little bit about process control, that how process gets created, how it exits. And then we took one case study regarding Unix process and we discussed that also. Fine. So all in all, we discussed the idea about the process. Now we are going to discuss processor scheduling. In fact, we don't call it process scheduling, we call it processor scheduling, because scheduling we normally do for a resource and not for the entity which uses that resource. Okay, so we need to do scheduling for the resource itself. And what is the resource that processes are using? The common resource that every process uses. I'm asking you, what is the common resource that every process is using? And that is processor. Memory is correct, that's true. But currently we are going to discuss processor scheduling, CPU or processor, right? And again, as we discuss that we are going to restrict our most of the discussion to the uniprocessor system, single processor, right? So this is the topic where we are going to discuss how single processor will be allocated or assigned to different processes so that they can execute. So with that, let us start. What is scheduling? So an OS must allocate resources amongst competing processes. First of all, there are resources and there are different processes. So OS needs to handle it. We know that OS works as a resource manager and it has to handle the allocation of these resources to process. The resource provided by a processor is execution time. Okay, so what resource, if we do not consider processor uh, as a resource, okay, at least the execution time which is given to this or which is provided to the process by processor, that can also be considered as resource. So I mean, all in all, it is processor which is a resource, and this processor time which is a resource is allocated by means of schedule. So there is a schedule. First of all, why schedule? Because we have a single processor. At a time only one process can execute, but we have many processes in our system at any point of time, and we want all of them to run, but they cannot run at the same time. So there will be a schedule, and based on that schedule, processor time will be assigned to each process and they will execute. So aim of scheduling is to assign processes to be executed by the processor over time in a way that meets system objectives. In a way that meets system objectives. So what is the aim of this scheduling? The aim of scheduling is to provide this processor time in such a way that it meets certain system objectives. And what kind of objectives we want to meet? Like response time, throughput, and processor efficiency. These are some of them. These are some objectives which we want to meet while assigning processor to the process. Response time, what is response time? Are you getting the meaning of this word? Can you guess about this? What can be this response time? Any idea? No, it is not time taken to complete a process. No, it is the time elapsed between the process creation and the first response that you get from that process. The first response that you get from that process, that is response time. It means your process has started working and you get some response out of that. May not be completed, but you started getting some output or some response from that process. So that is called response time. Then there is a throughput. What is throughput? Now, in general, what is throughput? In general, what is throughput? Any idea? Throughput is generally, in general, it is a rate of job completion. It is a rate of job completion. So here process is a job. Every process is one job. And throughput is nothing but how many processes can be completed in a unit time. And that unit can be anything. It can be 1 second. It can be 1 microsecond, whatever. What is the number of processes that can be completed, okay, on average in the given unit time? And then processor efficiency. Processor efficiency means processor should not be idle and it should be utilized at its full, right? So that is processor. So these are some objectives that need to be met when we assign processor to processes. Now the scheduling objectives, again we will go in little detail of the scheduling objectives. The scheduling function should share time fairly among processes. That is required. Whatever time is there, it should be shared fairly among processes. It should prevent starvation of a process. Now, what is starvation? What is the general meaning of starvation? Deprive of food, correct. So here, deprive of food, instead of that, we can say deprive of processor time. Okay, it is deprive of processor time. So that should not, it should not happen that any one process is never assigned processor because there are some other higher priority processes. That should not happen. So that is the another objective of scheduling. So scheduling must be done such a way that it prevents starvation of any process. Use the processor efficiently, we just discussed, right? It should not be idle, and most of the time it should be executing some processes. So that is processor efficiency. Have low overhead, okay? There should not be much job which increases the overhead. Like process switching is one kind of overhead. When you assign time to one process, and now if you take that processor back from that process and now you give it to another process, that is overhead, one kind of overhead. So this overhead should be lowered. And then prioritize processes when necessary. Okay, another scheduling objective, that if there are certain processes which are of very high priority, then your scheduling algorithm, whatever algorithm you use, it should prioritize those processes whenever it is in the need. Right? So these are some objectives of scheduling. Are you getting up to this point? Yes. Good. Then what are the types of scheduling? We discuss about objectives of scheduling, but then what are the types of scheduling? So mainly there are 4 types of scheduling. Okay, long-term scheduling, medium-term scheduling, short-term scheduling, and IO scheduling. IO scheduling is the topic for which we will cover when we will be discussing about IO. Currently, we are discussing processor scheduling. Okay, and first 3, these are the different types of processor scheduling. Long-term scheduling, what it does, it takes the decision to add to the pool of processes to be executed. Of course, we will be looking at this in little detail. Medium-term scheduling, it takes the decision to add to the number of processes that are partially or fully in main memory. And short-term scheduling, the decision as to which available process will be executed by the processor. So out of these 3, long-term, mid-term, and short-term, throughout this chapter, we'll be discussing about short-term scheduling, and that is also called dispatcher, process dispatcher. Okay, short-term scheduler or process dispatcher, and that is the discussion of that is the topic of the discussion of this chapter. This is chapter number 9 from your book, okay, that I have started. Long-term scheduling and medium-term scheduling, or you can say long-term scheduler and medium-term scheduler, they are more with the memory, Okay, they work more with the memory, and that is more the purpose of this scheduling is to manage memory also, to work with the memory. So when we will be discussing memory, you will be getting some idea of this. But throughout this chapter, we'll be discussing more on short-term scheduling. So let us see little bit about this long-term scheduling, medium-term scheduling, and short-term scheduling. IO scheduling will be discussing when we will discuss IO. So long-term scheduling is performed when a new process is created. So whenever a new process is created in your system, at that time, long-term scheduler comes into the picture. This is a decision whether to add a new process to the set of processes that are currently active. Now, if you remember state transition diagrams that we are going to discuss little late here, see, I hope you remember the state transition diagrams. Do you remember this? Okay. So whenever new process gets created, there are two places where you can put this new process, either directly in ready state if there is enough memory, or you can put it in ready suspended state if there is not enough memory. And when I say memory, I'm talking about primary memory, RAM. So if there is no enough primary memory, you can put it in ready suspended state, which is in the secondary memory. But then this is the job of long-term scheduler. When newly created process will get inside the system, either in ready state or this state, ready suspended state, that decision will be taken by long-term scheduler. That decision will be taken by long-term scheduler. And then again, nowadays the processes that we create, I mean, whenever we work with our systems, they are mostly interactive processes. Mostly, very few jobs that we do in the batch mode. That okay, you submit the job, you forget about that, and you finally get the output. Batch jobs are very less nowadays. Most of the jobs are interactive jobs. But this long-term scheduler, whether it is a batch job or it is interactive process, it will decide when a job will enter, when a new process will enter in the system. Maybe process is created, but whether it will enter in this ready state or ready suspended state, that will be decided by long-term scheduler. So that is the job of long-term scheduler. Then comes medium-term scheduling. It is a part of the swapping function. Now, if you remember, swapping happens between two different states, ready and ready suspend, and another is block and block suspend. I hope you remember those states. Do you remember those two states? Ready and ready suspended, blocked and block suspended. In last lecture, we discussed these states in Unix state transition diagram also. And that is nothing but swapping, because if you go from block to block suspend, you are putting your process from main memory to secondary memory. And if you go from ready suspend to ready, then again you are bringing it back from secondary memory to main memory. That is swapping. So medium-term scheduling is a part of this swapping function. This is a decision whether to add a process to those that are at least partially in main memory and therefore available for execution. Now, whenever swapping happens, fine, you put your process in secondary memory. Let's say when you go from block to block suspend, you are putting your process from main memory to secondary memory. But when you do so, still at least process table entry, some kind of attributes of that process, they must remain in main memory. Okay, and based on that, some decision will be taken. So this swapping, you can see that medium-term scheduling comes into the picture either when you move from ready suspend to ready state. So medium-term scheduling, actually here there should be two-way arrow. Mostly we put block to block suspend. Very rarely we put process from block suspend to block. Okay, but this is regarding medium-term scheduling. Okay, this is regarding medium-term scheduling. So when you swap a process, at that time, medium-term scheduling algorithm is used, or medium-term scheduler performs that job. And then finally, short-term scheduling is the actual decision of which ready process to execute next. So that is the actual decision. Which ready process will run next? That is the decision of short-term scheduler. That is the decision of short-term scheduler, and that is called process dispatcher. That is also called process dispatcher. So this is how you can see where each type of scheduling algorithm is used in this process state transition diagram. So this is relation between scheduling and process state transitions, and that will give you some idea where this scheduler plays its role at which point. And as I just discussed, throughout this chapter, we'll be focusing on different strategies or algorithms which are used for short-term scheduling. So we'll be discussing on this part. Again, this is the similar thing. It is showing where every scheduling algorithm is used in a queuing form. Otherwise, it is nothing but states. See, ready queue, ready suspend queue, block suspend queue, and block queue. And this is queue for the newly created jobs. This is a queue of the newly created jobs. Okay. So now you can see here, short-term scheduling, it is used when you need to dispatch a process from ready queue to processor. From ready queue to processor, at that time, this new short-term scheduling algorithm is used. So that is dispatcher. Medium-term scheduling, it is used when a ready process move to the ready suspend process, or ready suspend process moves to the ready queue. In any case, medium-term scheduling is used. Similarly, when blocked process moves to the block suspend queue, then again medium-term scheduling is used. Okay. Then you have long-term scheduling. So whether it is a batch job or interactive user process, whether it will enter in this ready queue or ready suspend queue, that decision will be taken by long-term scheduler. That decision will be taken by long-term scheduler. So this is the same thing using queuing diagram. I hope this makes sense to you. Does this diagram make sense to you? Okay. Another thing, I mean the same thing in a different form now. This is nesting of scheduling functions. Now you can see that again it is the same thing here. These are the states: running, ready, and block state. Here you have block suspend and ready suspend. And this is our new state and exit state where long-term scheduler comes into the picture. For this two states transition, medium-term scheduler comes into the picture, and from ready to running, short-term scheduler comes into the picture. So this is the same thing again and again, but in a different ways, right? Little bit about long-term scheduling. So we'll be briefly discussing this long-term scheduling and short-term scheduling, and then after we'll be discussing more on short-term scheduler. So long-term scheduling determines which programs are admitted to the system for processing. That is what we have seen. And it may be first come, first serve. This is the simplest possible strategy for long-term scheduler. Whenever long-term scheduler has to decide that when and which process will enter into the system, whether it is ready state or ready suspend state, most of the time, the simplest strategy that can be used is FCFS, first come, first serve, normal queue. Or if not FCFS, what else it can be? Or according to criteria such as priority, IO requirements, or expected execution time. Now, priority, still it can be understood that, okay, fine, priority can be known before. But for a process that you are going to execute, you are going to execute the program, the whatever program or application that you are going to execute as a user, can you predict how much IO will be required by that process, or what would be the expected execution time of that process? Is it possible to predict these quantities? What do you say? When you start working with, let's say, Word program, okay, or some other program, maybe some editor, can you tell the system before you start the process, can you tell the system how many IO you will be going to do, or what would be the expected execution time? Is it possible to? No, it is not possible. But that is not possible for interactive processes that we are creating right now, right? Currently, whatever we work with our system, they are interactive processes. But in case of batch jobs, just think about batch jobs. If you remember batch systems, batch processing system, there it was possible. Initially, when you submit a job, at that time, you can tell that, okay, these are the IO requirements and these are the expected execution time. So that is for batch jobs. So if these are some of the criteria which can be used by long-term scheduler to decide that which process goes into the system. Fine. So that is one thing. Purpose of this long-term scheduling. What is the purpose of this long-term scheduling? Why we need to perform long-term scheduling? Why not that whenever process created, why not to enter it into the system? Let's directly put it into the system. Why to hold it back? So the reason is controls the degree of multi-programming. That is the reason, to control the degree of multi-programming. Because if you allow more number of processes to enter in the system, less percentage of time each process will be executed. Definitely, there is a single processor, and if there are more processes, then less amount of time from that processor will be given to each of these processes. So you can, this long-term scheduler, it is there to control degree of multi-programming. In fact, not only processor time, but even if, memory, okay, depending on the memory that is available, you also need to decide that whether you should allow new process to be created. Okay, have you ever observed in your system, when you are working with your system, sometimes you try to open a process, open a application, but if your system is heavily loaded, it denies. It won't allow you to open that. Have you observed this? Because though nowadays memories are very large, but still, if you might have observed this kind of stuff, that you are trying to open a new process and it is not allowing you to open that. Yes, anyone? Fine. So that is one reason, because there is some program in the OS which decides whether I should allow more processes in the system or not. Okay, that can be the reason. Then medium-term scheduling, it's parts of the swapping function. We know that swapping in decisions are based on the need to manage the degree of, so that is also one reason. I mean, to manage the degree of multi-programming. You are not controlling the degree of multi-programming, but whatever processes are already there, this medium-term scheduling helps to decide whether swapped out process should be brought into the system. That is what medium-term scheduling decides. And finally, short-term scheduling. So it is also known as the dispatcher. Short-term scheduler is known as the dispatcher, not scheduling, but short-term scheduler, it is known as the dispatcher. And it executes most frequently, because the most frequent decision that OS needs to take, that at a time which process will run or which processor will move from ready to running state, that is the frequent decision, and that is taken by the short-term scheduler. And when this short-term scheduler gets executed, when dispatcher comes into the picture, whenever there is a need for process switch, at that time short-term scheduler or dispatcher comes into the picture and it takes decision there. And when process needs to switch, we discussed that in the last chapter. When process needs to switch, there can be different reasons for that. Either process is completed, there is some interrupt, there is some time completion. I mean, whatever time was allocated, that is over. Okay, there is some need from the operating system to kill your process. There are some signals from other processes to your process. So these are the possible reasons because of which process needs to switch. And whenever process needs to switch, dispatcher comes into the picture and it will decide if this process is going out, whether it is going in block state or ready state, which new process or which process will run next. That is what dispatcher will decide. And it's a frequent decision. So are you getting up to this point what we are discussing and in which direction we are going? Are you getting the idea? I know you are busy in your attendance, but yeah, fine. So this is overview, right, about the different types of scheduling. Now, whenever we do scheduling, as we discussed, there are certain objectives. Okay, there are certain objectives, and these objectives are based on certain criteria. So there are two types of classification of this short-term scheduling criteria. One classification is, again, now we are going to discuss everything regarding short-term scheduling. Forget about long-term scheduling and medium-term scheduling for now. Just forget about that. And now we are starting our discussion on short-term scheduling. So there are two criteria that you can compare and that you can use while deciding your scheduling strategy. Okay. While deciding this scheduling strategy, there are two criteria that you can keep in your mind. One is user oriented and another is system oriented. Now, user means you who is working with the system, and system, that means your operating system and your hardware system that you have, your computer. So the scheduling criteria, it is by user perspective or by system perspective. When it is user oriented criteria, as a user of your system, what is your biggest expectation from your machine? When you work with your machine, what is the biggest expectation that you have from your machine? Tell me, when you work with your machine, with your system, what is the expectation that you have? No waiting time, right? It should give response as quick as possible, isn't it? So response time is one possible criteria from user perspective. So the scheduling strategies that you are going to decide, I mean, not you, of course, it is already decided by the operating system, but the designer of the operating system needs to keep this in mind, that whoever is going to use the system where this OS is going to be installed, the user requirement is less response time. Okay, it should be quick. So that is one possible criteria. Another possible criteria is from system oriented, by systems perspective. And what is system perspective? There should be effective and efficient utilization of the processor. So OS designers, they need to keep in their mind while deciding the dispatcher strategy, they need to keep in mind that the processor should not be underutilized. It should be efficiently and effectively utilized. So these are the two possible perspectives by which the short-term scheduling or short-term scheduler strategy should be decided by OS designer. There is another type of classification of this criteria. One classification was user versus system. Another classification of this criteria, it is performance versus non-performance. It is performance versus non-performance. So there are certain criteria which are performance based and there are certain criteria which are not performance based and they are qualitative. Okay, they are qualitative. So what is performance based or performance related criteria? See, this performance related criteria, they are quantitative. You can easily measure them, like throughput, response time. They can be easily measured, right? But what are the non-performance related? Okay, can anyone guess about this? I haven't mentioned it here. Non-performance related criteria which needs to be kept in mind by OS designer while designing dispatcher. Any idea? Efficiency. Don't you think that efficiency is part of performance? Because that is the performance of your system, right? Non-performance means what? Like basically it is the satisfaction kind of stuff that you get through your system. Okay, let me give you a simple example. When you do certain job on your system, you expect that every time when you do the same job on the system, it should take same amount of time, regardless of how many other processes are running. So that is one possible non-performance related criteria. Okay, every time it should take same amount of time, regardless of how much load is there on the system. It is like, you know, something like okay, I mean, I can give you some example like home delivery of some items. If you are purchasing some item online, now when you purchase some item online during festival season like Diwali or Christmas, you may face some delay in the delivery of your item, isn't it? Has that happened with you? While Diwali or Christmas, if you order some item, you may face some delay. Your item may be delivered little late. But if you order item in other days, non-festive days, okay, you get your item very quickly. Have you faced this kind of situation? Okay, but what is your expectation? What is your expectation? Whether it is Christmas or Diwali or whether it is a non-festive days, I want my item on time, right? So that is your satisfaction, and that is non-performance. That is not related to performance. Why? Because they are, you know, they are delivering the items as per their capacity and their performance is good. But the only point is you may not be satisfied because there is more load on them, right? And their performance is not affected by that. Only your satisfaction is affected by that. So I hope you are getting the idea what is non-performance related stuff. Are you getting some idea what is non-performance related criteria? And definitely it is difficult to you know, quantify and to measure that, right? You cannot measure satisfaction. Of course, there are some mechanism like feedback mechanism in real world. Let's say Amazon is through Amazon you are facing this problem, so Amazon may take your feedbacks, and based on that it may decide that okay, with during festive season I need to increase my staff or something like that, right? That is possible, but otherwise it is difficult to measure directly. Fine. So now let us discuss some interdependent scheduling criteria. So we have seen the categories of this criteria, two different categorization. One is user versus system, another is performance versus non-performance. But now let's discuss some of these criteria which are interdependent, like some of the criteria which are user oriented and performance related. User oriented as well as performance related. So these are the three such criteria. Turnaround time. One is turnaround time. This is the time, this is the interval of time between the submission of a process and its completion. What is this? Time between, it is the interval of time between the submission of a process, that process is created or it is submitted in the system, and it's completed. So that elapsed time is turnaround time. So it includes actual execution time plus time spent waiting for resources, including the processor. Because it is possible that, see, it is not going to happen in multi-processors, in multi-programming system, that you start creating your process, you created your process and processor will execute that first and then after it will take another process. It is not that way, right? It is time sharing system. Processor time will be shared amongst different processes. So this turnaround time is actual execution time that your process has taken plus waiting time. And this is an appropriate measure for a batch job. This turnaround time, it is an appropriate measure for a batch job. Why appropriate measure for a batch job and not for not for this interactive processes that we are using? Okay, can you guess why? Why this is the better or appropriate measure for batch jobs and not for interactive jobs? Can you guess why? Because in interactive jobs, wait time, it depends on user interaction. See, if you are not providing some input which is required by your job, which is required by your process, and you are not providing that input for a long time, maybe you have gone for break and it was asking some input and you have not provided that, so that is going to affect the turnaround time, because waiting period will become more, isn't it? What do you say? Yes or no? Right? So that is more appropriate measure for the batch job. Then comes response time. So for an interactive process, this is the time from the submission of a request until the response begins to be received. First response, you start receiving the first response. So that is the time between that. Often a process can begin producing some output to the user while continuing the process, the request. Still your request is not completely processed. It is still in the process, but at least you start receiving some output. Thus, this is a better measure than turnaround time from the user's point of view. Okay. So the scheduling discipline should attempt to achieve low response time and to maximize the number of interactive users receiving acceptable response time. And the biggest example of this kind of response time required thing is web browsing. Whenever you try to browse the internet, you always expect as soon as you hit enter, you should get the response. The page should be displayed, isn't it? So if you, let's say you are doing some online shopping through net, through internet, right? You are having Amazon website account, you are doing that. But see, that is interactive, because at every stage you need to provide some input. Okay, let me select item, let me select the mode of payment and all this. So every point you need to provide some input. But what is your expectation? As soon as I provide one input, whatever response of that input is there, it should come immediately to me. So you do not want to wait. So that is called response time. One input you provide, one interaction you do, and you want to get response of that. I hope this example helps you to understand the idea. Yes. And then deadlines. That is another criteria. When process completion deadlines can be specified, the scheduling discipline should subordinate other goals to that of maximizing the percentage of deadlines met. Mostly these deadlines, they are there in the real-time systems, real-time operating systems, embedded systems, right? So they are there in, mostly they are there in real-time systems. So from our point of view, that the type of systems that we are using, for us, response time is the more important criteria, we can say that. Turnaround time is more important for batch processing. Deadlines are more important for real world systems, real world operating systems. But for the OS that we are using for our jobs, response time is more suitable. Then again, user oriented, but not performance based. These are the performance based. You can measure the performance. But these are the user oriented and non-performance based, like predictability. The example that I just gave you actually. Okay. A given job should run in about the same amount of time and at about the same cost, regardless of the load on the system. My item should be delivered to me, whether it is festive season or non-festive season, right? That is one example. A wide variation in response time or turnaround time is distracting to users. So if you have wide variation in the response time, let's say one page gets loaded in a quick time, but then after next page is getting delayed, okay, let's say it is taking more time, 1 minute or so, of course it is not acceptable. It may signal a wide swing in system workloads or the need for system tuning to cure instabilities. This type of criteria, when you face this kind of problem, it is a signal that your system needs to be taken care of. It needs to, system administrator needs to take some steps on that. Then system oriented, which can be measured, that is performance related. So throughput is one of them. This is not by user's perspective, but this is by system perspective. Throughput and processor utilization. Turnaround time. Okay, there is a question that example of turnaround time. Basically, it is most suitable for batch processing. For an example, let us say you have written one program, web crawler program, suppose. Okay, you have written web crawler program. Are you aware of web crawling or web scraping? Right, where once you written your program, you provided all required input at the same time, and then after you are not going to interact with that program until unless it is completed. You are just going to check its result. Okay, so as soon as you start your program and when it ends, that is turnaround time of that, because then there is no user interaction with that program. That is one kind of batch program. So for that, how much time it has taken to complete that job, that is turnaround time. I think this should help you to understand the idea, right? So now we are discussing system oriented performance related criteria like throughput. So the scheduling policy should attempt to maximize the number of processes completed per unit of time. As I told you, unit of time can be anything. This is a measure of how much work is being performed. This clearly depends on the average length of a process, but it also influenced by the scheduling policy, which may affect utilization. How? When we will discuss different scheduling algorithms, you will get some idea. Processor utilization is another criteria. This is the percentage of time that the processor is busy. Okay, for an expensive shared system, okay, if the system is being shared, this is very significant criteria, because if multiple users are sharing the system, it should not remain idle for long time, so everyone gets the enough job get done, right? A single user systems and in some other systems, okay, the systems that we use, a single user systems, in some other systems such as real-time systems, this criteria is less important than some of the others. Like in real-time system, deadlines, to meet deadlines is more important than the processor utilization, because real-time systems or embedded systems, they are made for specific purpose. So if processor is not utilized properly, it's okay, but the point is job must be get done as per the deadline. The simple example of real-time system that I can give you is missile system, the operating system that you have in missiles. What is more important, processor utilization or it should meet this deadline? Yeah, so what is more important? Definitely meet deadline, right? If it misses the deadline, if it misses its time, then missile can create some destructive scenario. So these are the two system oriented and performance related criteria, but processor utilization is important in shared systems, multi-user shared systems, right? But they may not be that important in real-time systems. And finally, system oriented, which are not performance based, okay, like fairness. In the absence of guidance from the user or other system supplied guidance, processes should be treated the same and no process should suffer starvation. That is fairness. Your processor should be given fairly. It should be assigned fairly to all processes. There should not be starvation of any process. So that is one system oriented but non-performance based. Enforcing priorities. When processes are assigned priorities, the scheduling policy should favor higher priority processes. So now these are two, this fairness and enforcing priorities. Actually, these are the two contradicting criteria. If you try to be fair, you will assign same amount of processor time to every process. But if you want to use priorities, if you want to enforce priorities, then you will assign higher amount of time of processor to the high priority processes. So these are the contradicting, but of course at a time you cannot meet both. At a time you cannot meet both the criteria. And then there is a balancing resources. The scheduling policy should keep the resources of the system busy. Processes that will underutilize stressed resources should be favored. Now this is again contradicting words. Underutilize stressed resources. So those resources which are heavily being used right now in the system, at that time you should assign processor time to those processes which are not going to use those resources which are currently under heavy use, so that it will relax the use of those resources. So that is going to balance it out something. Okay, so this criteria also involves medium term and long term scheduling. Fine. Why this is more involved with medium term and long term? Because memory is one of them, one of the resource, and this medium term and long term scheduling, it is more inclined towards memory utilization. So these are some system oriented, I mean by system perspective, these are some important criteria, but these are not performance based, these are non performance based. Are you getting all these criterias? Are you getting the idea of these criteria that we are discussing? Yes. So let us discuss a little bit about priorities. Though you understand priorities, okay, scheduler will always choose a process of higher priority over one of the lower priority. Okay, so this is the case. You can see that have multiple ready queues to represent each level of priority. You can do this. What you can do, whatever ready queue you have, that ready queue you can have multiple ready queues instead of one ready queue, and each ready queue has those processes which are of same priority. So whenever, let's say this is the ready queue 0, which has the highest priority processes, then ready queue 1 which has less priority than this, then you have ready queue n which has less priority than this. So this is how you can manage all priorities, all processes with different priorities in ready queue. So whenever dispatcher needs to decide that which process it should dispatch, it will first go to this queue and take the first process from this queue, because all the processes in one queue, they are of the same priorities. They are of the same priorities. Okay, so it will become easy for dispatcher program to decide that which process will go next. It will first find a process in this. If there is no process in this priority queue, then it will go to the next queue, and then next, likewise. Okay, so this is priority based scheduling. Again, not all algorithms are priority based. Then we discuss one term called starvation. What is starvation problem? So if your scheduler, your dispatcher, it works based on priorities. Just think that, let's say you have this RQN, or let's say RQ3. Let's say we have 3 ready queues. But you observe that at every instance of time, at any instance of time, not every, in fact, at any instance of time, at least there is one process in this queue or this queue. Whenever dispatcher needs to decide which process will run next, at least one process is always there in any of these two queue. What do you think? When this process will get chance? When the process in this queue, ready queue, will get chance to run? But what I say, you take any amount, any instance of time, at least one process is always there in this. Okay, so that is the starvation, because this process will never get chance to run. This process will never get a chance to run. If I give you example of some family, royal family, right? If you have your father there, you will never become king. Even after your father, if you have elder brother, he will become king and you will never get chance to become king, right? So like, you can never become king because you have some elder people in your family, in royal family, who is there and they will become king. Even if your father has, I mean, if that father of that particular guy has passed out, his elder brother will become king and he won't get a chance. Okay, so this is starvation. You can never become a king. So this process will never get chance to run, because at any point of time there is at least one process in any of these two queues. That is called starvation. So lower priority may suffer starvation if there is a steady supply of higher priority processes. What is the solution? What is the solution? Allow a process to change its priority based on its age or execution history. Okay. Now what can be done, that whenever some process has spent some time in the system, its priority should be lowered down, because it has utilized some amount of processor. So now its priority should be lowered down. So the lower priority process, it will get chance at some point of time. So that is what feedback queue kind of stuff that we will discuss later. Okay, but that is one possible solution to starvation, that you can change the priorities. You can change the priorities runtime based on some criteria like age or execution history. Does this make sense? Okay. So what are the various scheduling policies? These are the various scheduling policies that we are going to discuss, and they are there in your book. First come, first serve, the simplest strategy, round robin, shortest path next, shortest process next, shortest remaining time, highest response ratio next, and feedback. Out of this, round robin and feedback are most practical strategies. Round robin and feedback, these are the practical strategies. Okay, others are theoretically fine, they are there, but at least they are not that practical in our current systems that we are using. Maybe they are suitable for some other type of systems, but at least for those systems, time sharing systems that we are using, they are not that practical. But we will be discussing them, as it is a, we need to understand the different strategies, and we will compare them also, right? We will compare them. Now there is something called selection function. Okay, so basically, based on the strategy that you are having in your system, the selection function determines which process is selected for execution. So basically, this is nothing but the strategy. The function may be based on priority. Now this selection function, maybe it may be based on different criteria. It can be based on priority or resource requirements or the execution characteristics of the process. So number of criterias are there based on which selection function works according to the strategy. Now, before we start actual discussion of this scheduling strategies, let us understand few terms, where W represents time spent in system so far, that is waiting. Basically, it represents waiting time. E, it is time spent in execution so far. E is the time that process has spent in execution, that duration of, for that duration it has already executed. As total service time required by the process. So as and when we come across this example, we'll be discussing this. Turnaround time, that is service time plus waiting time, or you can directly consider this finish time minus arrival time. Both way it is possible depending on the type of example that you have. You can either work with like service time plus waiting time, or you can say finish time minus arrival time. That is turnaround time. Then there is normalized turnaround time also. Okay, normalized turnaround time, that is TR, that is normal turnaround time divided by service time. Okay, so again, these are some mathematical calculations that we will be discussing more on when we will be discussing particular strategy. This is just the overview that I am trying to give you. And finally, there is something called decision mode. It specifies the instance in time at which the selection function is exercised. So whenever selection function, whenever dispatcher needs to decide that which process will go next based on the strategy that is implemented, okay, there is a decision mode that is non-preemptive or preemptive. Now what is that? Non-preemptive versus preemptive. Non-preemptive, what is non-preemptive? Once a process is in the running state, it will continue until it terminates or blocks itself for IO. You will never, I mean, you means OS will never remove that process from running state and put it in the ready state. No, except only in two cases that process will be removed from the running state. Either it gets blocked itself by waiting on some IO or some other event. Okay, then only that process will be removed from the running state, or it has completed its job, then only it will be removed from its running state. But otherwise, OS will never remove it from the running state. Okay, that is non-preemptive. That is non-preemptive. And what is preemptive? Currently running process may be interrupted and moved to the ready state by the operating system. Okay, and when that happens, preemption may occur when new process arrives. Like if higher priority process arrives, then it is possible that if OS design is such a way that it gives it gives more chance to higher priority processes. If new higher priority process arrives, then the running process may be interrupted. It may be removed from the running state and new process will be given a chance. Or some interrupt occurs, or periodically, like you have decided that every process will get some amount of time on the processor, and then after it will be removed from running state and put it back in the ready state, though it is still capable to run. Round robin is one such strategy where every process is assigned some amount of time. Then after, even if process is still able to run, it is not blocked, it will be preempted and put it back into the ready state, and new process will be dispatched to run. That is preemptive strategy. So there are two strategies, two decision mode, non-preemptive versus preemptive. And which decision mode should be preferred? Preemptive. Which decision mode should be preferred? Preemptive. Why? Preemptive policy may increase overhead. That is a problem. Actually, that is a problem, because every few milliseconds or microseconds, you are going to switch the process, which is very heavy job in terms of computing, in terms of processor wastage. Okay, so preemptive policy may increase overhead, but prevents one process from monopolizing the processor. If there is a very big process which needs to perform a long job, okay, and it is never going to block because it doesn't require any IO, let's say, so it won't be removed from running state until it is completed, and that is going to hold all other processes back. It won't allow any other process to execute unless it gets completed. So OS normally prefers preemptive strategies. Okay, OS designers, they normally prefers preemptive strategy. But preemption, again, in which case preemption should be performed, it depends. It depends what kind of preemption you allow. Okay, so that is also what we are going to discuss. So this is about introduction of uniprocessor scheduling. We have discussed theory part. From the next lecture, we'll start discussing the actual strategies, the different strategies that I have listed here. Okay, we will be discussing each of these strategies in detail, and then we will compare them also, right? Any question up to this point? Any question up to this point? Okay. So if there is no question, what I can do now, I can jump to that practical aspect. We have few minutes, 10 minutes at least. So let us discuss that little bit. Okay. Is my screen visible? Fine. So now let us discuss the process states in Linux process. Yesterday we discussed process states in Unix system, right? That was pure theory part. Now practically if we see what are the possible process states in Linux system, again these states that I am showing here, they are for the older kernel. Newer kernel has added one more state that I'll be discussing, but just to get an idea, in Linux running and runnable, it's a common state that is called R. Either process is running or it is runnable. Why? Because it is using round robin, and in round robin it is like same. So we'll discuss that. But in Linux it is running and runnable, common state, that is R state. Okay. Then there are two types of sleeping state or waiting state. These are the two type of waiting state. Fine. One is uninterruptible waiting, another is interruptible sleep. Like when your process is waiting for some IO, it is uninterruptible. It cannot be interrupted. Okay, until unless that IO event completes, that process cannot come out of this sleeping mode. And there is some interruptible sleep, like programming it programmatically. You are blocking some process so that it is, let's say it is waiting for some event, it is waiting for some other process to wake it up. We'll see that in producer consumer, one process is waiting for other process to do some job. Okay, so if that process completes its job, it will send some signal to this process that okay, now you come up, you wake up and you can start, something like that. So that is possible. Interruptible sleep, it can be interrupted, some signal can be sent to this process, and when that signal comes, it will go back to running state. This is uninterruptible sleep. This is called D state. This is called S state. This is R state. Then you have stop state. You might have started some command on your command prompt in Linux, and if you say Control Z after that, immediately that process will be stopped. It is something like suspended, not exactly like that, but it is similar to that suspended kind of state. Okay, and there is signal which will be given to this stop state, that is continue, then it will continue and come back in ready state. Then finally you have zombie state. So when process completes, when you call exit, process completes, but still some process data structure is there in the system, and that is the zombie state. So these are the 5 stages or 5 states of a process in Linux system: D, S, R, T, Z. In newer versions of this Linux kernels that I have, now they have added one state called I, which is idle state. It is kind of blocking state. Not exactly blocking, but idle means it is not running. Okay, it is idle. It is not being executed. It is not blocked. It is not waiting for an event, but it is not running, right? Idle state. So that is there. So this is all about that states. And these are some commands that we will try to use to understand the processes. Let me try this. Okay, one is ls cpu. If you want to get information regarding your processor that you have in your system, ls cpu will give you that information. Okay, here you can see that model name is Intel. My processor is Intel processor, and vendor ID says that it is genuine Intel. And what else I want to see here? Just a minute. These are the cache information. How much cache is there in the processor? These are the registers or flags. Sorry, these are the flags, program status word, if you remember. So these are the status words or the flags that is there in the processor. Then the number of cores. Where is that? Yeah. Total number of CPUs are 4. In this machine, there are 4 CPUs. Address size is 39 bits physically, but with virtual memory, it is 48 bits. Byte order is Little Indian. And number of cores per socket is 2. Okay, there are 2 cores and each core contains 2 threads. So total 4 CPUs likewise. So this is the command which helps you to see the architecture of your processor, the information regarding your processor. Then if you want to see about processes that are right now there in the system, you can use this ps-aux. Of course, ps itself is a command, but it won't give you much information about all the processes. If you want to see all the processes from all the users which are running on this system, you can use this command ps-aux, and it will give you different processes information. And what information it provides? First of all, it gives you which user has started that process. So currently I am the only user right now who is running, and the root user, that is system. Okay, so root, and you can see my name. I am the user who has started some process, right? So if I see, I can see Zoom. I should be able to see Zoom applications, Zoom process here. Can you see Zoom anywhere? Let us try. Yeah, see, I have started Zoom, right? And iState is also there, which is idle, and mostly this is applicable to kernel threads. So let us not get into detail of that, but so ps-aux is the command through which you can see all the processes, and what details you get: who is the user of that process, what is the PID, process ID, what is the percentage of CPU that is used by that process, what is the percentage of memory that is used by that process. Okay, virtualization and other things are there, terminal is there, state is there. So command, which command has started that particular process, so that is there. So if I say Zoom, I have started Zoom. Where is it? Zoom. Let us say Zoom. Which command I have started? I have started user bin Zoom command. Okay, it is there in this directory. Fine, and some other internal threads are created by Zoom, so it is executing this program. Similar command to this ps is top, which also provides, but ps will give you screenshot. At that time, whatever processes were there, it has given you information about that. Top is the continuously running command. Continuously, you can see that it is changing the screen because it is showing the recent information about the processes. If you add a new process or delete some process, that will go out of that list. So top is the command which give you more information, current latest information regarding the processes. Again, it gives you PID, the user who is running that, like Zoom. You can see Zoom. This is the priority. It goes from -20 to +20. This is the nice value, which we will see later on. Virtual memory uses. This is the main memory uses actually. Then you have shared memory, state of that process, SRI, you can see here, percentage of CPU, you can see maximum CPU is utilized by Zoom. Currently in my system, maximum CPU is utilized by Zoom because I'm working on that. And most of the memory is utilized by Zoom. And this is the command and total time which is taken, total time which is taken. This is the minutes, seconds, and milliseconds. This is the time taken by, okay, that particular process. This similar job, similar command is stop, which is similar to top, but it gives you more better kind of information. I mean, information is still same. Another utility which gives you similar information, stop. Okay, but that is there. So these are some commands, not all. I mean, of course, I have just given you 1 or 2 commands, but these are the important commands through which you can get the information regarding processes in your system, in Linux system. Okay. I have some system. Okay, let me just stop this for now. And let me briefly give you just a minute. And little bit about the system calls which are important with to work with processes. Like fork, it will create a new process. Exec, it allows you to execute other program in current process. Wait, it is allowing parent process to wait for child to be terminated. And exit, it allows you to exit the process. So these are the very important system calls that you need to work on. Maybe in next lab you will be working on this. I'll give you some assignments based on this. So what you do, you better go through this idea of fork, exec, wait, and exit. Okay, these are the system calls which you use to work with processes. And this is not all, again, this is not the exhaustive list. There are a few more. Okay, fine. So for today, this is all that I wanted to discuss. Let me stop.